I was just asked about the exams. I haven't started grading them because I have a big stack of other exams from a really big class that I was doing. I've just finished those, so I'm gonna get started on yours. I expect to finish them probably this weekend. So, shouldn't be too much longer. Today, we want to continue what we were doing on half angle identities and double angle identities, particularly half angle. That's the one we were doing before. And then we'll continue and do the next section, which is kind of a short one, on sum to product and product to sum formulas. We're actually getting towards the end of all these identities. How about that? And we'll say, recall these half angle identities. These are ones you should memorize, right? You should have that the sine of 1/2 an angle is equal to plus or minus the square root 1 minus the cosine of the whole angle over 2. And then the cosine of half an angle is plus or minus the same thing, except with this minus replaced with a plus. It's plus or minus square root 1 plus cosine x over 2. And then tangent of 1/2 an angle can be written as the quotient of these, right? And the square root 2 is canceling. This becomes plus or minus square root 1 minus cosine x over 1 plus cosine x. I think this is the easiest way to memorize these. We also have other half angle identities for tangent, but this tangent half angle is used so seldom at all that memorizing more than this one, I think, is not worth it. And this is the easiest one to memorize. So let's call those formulas 1, 2, and 3. And I just want to make sure that I do at least one more problem on these, on a couple parts of this. We said last time that we can now do, we can now evaluate trig functions of any angle that's half of an angle that we already know exactly. So for example, suppose I wanted to calculate the tangent of 105 degrees. I know I can do that because it's half of a special angle, right? And in fact, as part of that, you should realize that these half angle identities will now compute it exactly. Any sine, cosine, or tangent of an angle that's a multiple of 15 degrees. We said we could do all of those before with the sum and difference identities. Now you can also do them with the half angle identities, but in addition, you can also do half of any angle you knew. So if you can do it any multiple of 15 degrees, you can also do any multiple of 7.5 degrees. You can also do any multiple of 3.75 degrees and so on. I could ask you those on the test, but I'm not going to because it's too much fluster and fume. It takes up too much time on the test. The reason for asking those would be that calculators won't do those exactly. Calculators will do any multiple, a lot of them will do any multiple of 15 exactly. And I want you to check your answers. Do it by hand. Show me the work on the next test. And I'll grade you on that rather than doing half of an angle or something. Then you can also, since you can do 45-degree multiples, you can do any multiple of 22.5 degrees by doing half angle identities and so forth. Let's do this one. I know this is a multiple of 15 degrees because any quadrantal angle is a multiple of 15 degrees. This is the quadrantal angle 90 degrees, right? Quadrantal angle is where it comes out on an axis. Plus 15 degrees, so this must be a multiple of 15 degrees. As a multiple of 15 degrees, it's half of a special angle. This one, for instance, is 1/2 of 210 degrees. So that's how I think about these. This is 15 degrees from 90, so it's a multiple of 15. I know I can do it either with a half angle identity or with a sum and difference identity. If I use the half angle identity, then I use the tangent formula. I say this is plus or minus the square root of 1 minus cosine of the whole angle, 210 degrees, over 1 plus the cosine of the whole angle. And now, since I doubled the original angle, this is a special angle, and I can do this exactly on the unit circle, or if it's an acute angle, I can just use a right triangle. This one is not an acute angle, 210 degrees, so I'll figure it out. And then, by the way, is it plus or minus? This is the trick we mentioned it briefly last time. I want to remind you. You see 210 degrees cosine is negative there. Be careful, because you're not interested in this plus or minus goes with this tangent back here, not with this cosine over here. You're evaluating the tangent. The radical sign means the non-negative number that has this square. And then, so this will be a positive number. And then do I use plus or minus with it? 105 degrees is in the second quadrant, right? Over in the second quadrant. The sine is positive, the y coordinate, the cosine is negative, the x coordinate. So sine over cosine is actually negative. The tangent will be negative in this quadrant. And I'll scratch this out and I'll say this is in quadrant 2, the original angle, not 210 degrees, it's in quadrant 3. You might say, oh, 210 degrees, tangent is positive in the third quadrant. But we're evaluating the tangent of 105 degrees. All right, so use the minus because this tangent should be negative in quadrant 2. Now what do we get? We have to evaluate the cosine of 210 degrees. There's 180 and 30 more makes 210. Now we've got a right triangle down here, a reference triangle with sides, since it's a 30, 60, 90 triangle, 1/2 and square root 3 over 2 and 1. All we need for the half angle identity is the cosine, right? They all just use cosine. That's what makes it kind of easy too. The cosine is the x coordinate minus square root 3 over 2. So what we have then is that this tangent we're trying to evaluate is minus the square root of 1 minus a minus square root 3 over 2. Right? Cosine is negative over 1 plus negative square root 3 over 2. There it is exactly. But if you leave it on a test, I'm going to take 2 points off, not just 1, because there's a lot of algebra left. And one of the reasons I wanted to do this is we need to just practice a little more algebra. And I have another comment to make besides. You can't leave it like this because you've got compound quotients, right? So you have to get rid of those. And how do I get rid of compound quotients? I multiply through by the least common multiple of the denominators, right? The denominators are both 2, so I just need to multiply by 2 to get rid of them. I'll multiply the top by 2. The top is 1 plus square root 3 over 2. Multiply that by 2. And I'll multiply the bottom by the same, so I didn't change the quotient. Bottom is 1 minus square root 3 over 2. Now that gets rid of the compound quotients. 2 times 1 is 2. 2 times square root 3 over 2 is square root 3. 2 times 1 is 2. 2 times minus square root 3 over 2 is minus square root 3. And how do I deal with this? This one still isn't done. I said in some cases you can leave the square root of the square root in here for this class. When I count this not done, there's still at least a point off here. How do I get rid of this square root 3? I can't multiply top and bottom by square root 3. It'll not go away. It'll now multiply the 2. When you have a denominator that's a plus b square root c or a minus b square root c, these are called conjugates of each other. And whichever one you have, you multiply by the other one to get rid of the radical. So if I have a 2 minus square root 3, one in this case, I multiply the bottom by 2 plus square root 3 to get rid of the radical. Then I have to multiply the top by the same so that I don't change the quotient. So what I'm saying is this: I have minus square root 2 plus square root 3 over 2 minus square root 3. To get rid of the radical in the denominator, the bottom, I'll multiply both the top and bottom by its conjugate, 2 plus square root 3. So you see this gets pretty complicated in algebra, but it's necessary, right, to get the exact answer.
Okay,
Yeah.
where are you getting 210 from over here?
Oh,
I know it's a reference triangle, but I don't know how you're getting 210 exactly.
yeah, so you start off when you have an angle that's a multiple 15 degrees. Then twice that angle, in this case, twice 105 is 210. Will be a special angle. So what I do is I rewrite this one as 1/2 of twice its value. So 210 is twice 105, and then times 1/2 gives 1.
So you always multiply by 2.
Yeah, you always multiply by 2 and then put a half to cancel it. And then this is half of the special angle always. So multiple of 15, I put twice that angle times a half. Any other questions? Anybody online? You're welcome to. This is the key feature. Now it's half of a special angle, a half angle identity allows me to evaluate it exactly. And it's complicated. Once you figure these things on the unit circle and get an exact answer, there's still a long way to go. Look at this. So hope I don't run out of board, right? Now, however, since I multiplied top and bottom by the conjugate of the bottom, 2 minus square root 3 has conjugate 2 plus square root 3. Watch what happens. 2 times 2 is 4 by 4 out here. 2 times square root 3 is the outside, minus 2 times square root 3 is the inside, and minus square root 3 times square root 3 is minus 3. There's the denominator. And these two cancel, the radicals go away. In fact, the denominator in this case is just 1. All right. The numerator, not so. These are not conjugates, they're the same, so the radicals won't go away. 2 times 2 is 4, plus 2 square root 3, plus 2 square root 3 on the inside. There's another one, plus square root 3 is 3. What I have then is 4 plus 3 is 7, plus 2 of these and 2 more is 4 of these. So I combine these to become 4 square root 3, 2 of them, 2 of them is 4 of them. 4 plus 3 is 7. The bottom's just 1. Now I have it. It's minus the square root of 7 plus 4 square root 3. There's an exact answer. This actually isn't technically probably simplified. But I will accept the answer like that because actually going further than this using algebra is pretty complicated. Right? So that'll be an okay answer with the square root of the square root, but don't leave it like this with compound quotients or with a denominator that's not rationalized, all right? Now the comment, I said by the half angle identity, you can do any trig function of a multiple of 15 degrees. We only have 3 trig functions, sine, cosine, and tangent. How can we do the other 3? You just take 1 over these. If you want the cosecant, you just take 1 over the sine and use the sine half angle identity. That being said, another note, recall that also we can do all these multiples of 15 degrees using the sum and difference formula. So also, alternatively, we could use the sum or difference formula. We could put tangent of 105 degrees. If we can write 105 degrees either as a sum or a difference of special angles, remember special angle multiple of 30 or 45, then I can do this exactly with a sum or difference formula. And any 15 multiple can be done that way too. So I could write this as tangent of 60 plus 45 is the easiest, right? I could also write, I don't want to write 75 plus 30, but 75 is not special, but I could put 150 minus 45, and that would work also as a difference, and there's also others. All right, tangent of 60 plus 45. Now, this is a tangent x plus y. We can write this one. I think. We can write tangent of a sum of 2 angles, tangent of x plus y, recall, as tangent plus tangent plus with plus over 1 minus on the bottom, the opposite side of the bottom, tangent, tangent. This one's harder to remember. I had a harder time remembering this. But tangent of the sum is tangent plus tangent over 1 minus tangent. And we can evaluate this way because these are special angles. So you have an alternative on a multiple of 15 degrees angles. You can either do the half angle formula or you can do a sum or difference identity. But in addition, the half angle formulas will do half of these 15 degree angles and half of those and half of those. It'll also do half of any 45 degree angle, right? So we'll get 22 and a half degrees or half of that and half of that. All right, so here's these. Now, if you apply these formulas from the unit circle, well, actually, let's just use triangle. The special triangles for 60 degrees and 45 degrees, we recall. 60 degrees, we have square root 3 over 2 and a half. And we observe the tangent is this one over this one is square root 3, right? Tangent 60 is the opposite over the adjacent. 2's canceling gives you square root 3. Similarly, on the other special triangle, 45, 45, 90, you've got side square root 2 over 2, square root 2 over 2 is 1. On this one, the tangent of 45 degrees, then, it's this one over this one, adjacent over, opposite over adjacent. It's square root 2 over 2 over square root 2 over 2 is 1. So these are the two numbers we can put in for tangent here. We have square root 3 plus 1 over 1 minus square root 3 times 1. How about that? Oh, it's 1 plus square root 3 over 1 minus square root 3. And we can evaluate it this way. Now, how do we change this one? It's the same thing. A plus b square root c in the denominator. To get rid of the radical, we multiply both the numerator and denominator by its conjugate. We can multiply 1 minus square root 3 by 1 plus square root 3. And then we have to multiply the top by the same. The top was 1 plus square root 3. I just add in the opposite order. And I'll multiply that by 1 plus square root 3. So here's the same quotient. This one and this one. And I multiply top and bottom by the same thing. That won't change the quotient. And now I suppose I better erase these little triangles I just drew. Fortunately. I'll say we remember those already. Ooh, that's bad, huh? All right. And now when you FOIL, the denominator will get rid of the radicals because they're conjugates. 1 times 1 is 1. Then there's plus square root 3 on the outside, minus square root 3 on the inside. In fact, you don't even have to write these if you want. Outside and inside always cancel. Minus root 3 times minus root 3 is minus 3. And the top now is 1. Plus square root 3 plus square root 3 is 2 square root 3 using the outside and the inside. And then plus square root 3 is 3. What we have on the top is 4 plus 2 square root 3. And on the bottom, 1 minus 3 is negative 2. These canceled as we wanted. We're not done still. Still, there's a factor of 2 on the top and bottom. Be careful on this. Don't write this as negative 2 plus 2 square root 3. Factor the 2 out of the top, right? This is twice 2 plus 1 square root 3, right? This time this is 4. This time this is 2 square root 3. All divided by negative 2. I can put the negative out front at any time. Negative on the bottom or negative on the whole top can go out front. It all means the same thing. Now I can cancel the 2 with the 2. So this minus is this minus. And the answer is just minus 2 minus square root 3. All right. There it is. This minus distributes. Minus 2 and minus square root 3. That's what this is, believe it or not. It doesn't look like it, but if you were to simplify it, you could rewrite it like that. And what happens in a lot of cases is that if you do a half angle identity, you get an answer. If you do the sum or difference identity, you get an answer, and they don't look the same. But if you run it on the calculator, you'll find you get the same decimal. So these are alternative methods. And actually, this one can be reduced with a lot of complicated algebra. This is enough, isn't it? So let's leave it there, and I'll say you can leave a square root of a square root. Just don't leave radicals in the denominator, or unless it's simpler that way, don't leave these kind of radicals in the denominator. And don't leave quotients of quotients, right?
Which answer are we looking for in the back of the book?
Oh, it depends. That's a good question. I have not looked. This is all. I've only been assigning out of these sections problems from the UCO supplement. So you want to know what answer form is in the UCO supplement. If it's in the section on sum and difference identities, it will surely be this one because I used a sum and difference identity. If it's in the half angle identities, I don't know if this or this will come up. I'm not sure if there's enough examples to have differences show up. If it doesn't match the answer at the back of the UCO supplement, compute the decimal form and see if it matches. And if it matches the decimal form, then it's the same, just not written the same. Let me see if I can look on there and figure it out. 7.3, let's see if there's any of them that come out with, they leave them as square roots and square roots. But I said I would take those just to avoid unnecessary algebra. I think maybe that the answers, the problems on here just avoided that dilemma, but let's see. They may have given answers that don't need this kind of thing. Oh, too many pages. They left them in this form. All right. I should say we, I was actually on the committee who talked about these. I didn't make them up, but, yeah, so they went ahead and left them like this, not wanting to do the extended algebra also. At least on this problem I see here. There are a lot of them don't have answers in that section too. Okay, so there's some tricky algebra. I told you before, you'll be a good algebraist when you get out of this class. Now, there's a couple other things we should discuss on here because we've said every time we get a new set of identities, we also want to simplify expressions and be able to prove new identities with them. So there's some expressions to simplify in here. I want to make sure I did this one. Yeah, here we go. Example. This is number 9, part A. Suppose I said simplify the expression cosine squared 28 degrees minus sine squared 28 degrees. This section is on both double angle and half angle identities. So you have to figure out which one it is. Simplify, but do not evaluate. So they're saying simplify to a trig function. Don't evaluate. Here you have two trig functions. What can you do? The object is to know these identities by memorization well enough. You say, I've seen that before. Where did I see cosine squared minus sine squared? I recall this double angle identity, which we didn't put up yet today, but cosine of 2x is cosine squared x minus sine squared x. That's where I've seen it before. So if I just call this x, I notice that directly this is the cosine of 2 times 28 degrees, or the cosine of 56 degrees. So there's one example, but I wanted to do a trickier one here. This one says, suppose I want to simplify 1 minus 2 sine squared 17 degrees. How does that simplify? That was not so easy. Remember the tricks for this? We try algebra. If there's quotients and quotients, we get rid of it. If there's difference of two quotients, we can put them over a common denominator. We factor things out and cancel them. All that algebra. Then you can apply a trig identity, you know, and then you put everything in terms of sines and cosine. Well, two of those don't apply because there's no more algebra really to do with that. And so already in terms of just sine and cosine, in fact, just sine. So all I can do is try and apply a trig identity, but you go through those 3 steps and you try and figure it. Plus there's an additional step. They can only have one angle there, but there's also one angle. So the only thing you can do is try and think of a trig identity. What can I do with that? Whenever I see a square, I think sine squared. I could replace it with 1 minus cosine squared, but that doesn't look like it makes it easier here. Here's the trick on this one. If you replace 1 with sine squared plus cosine squared of 17 degrees, I'll leave off the parentheses here. It's done a lot to save writing. And then subtract 2 sine squared. That makes it more complicated just for a second. But then I realized, wait a minute, this one will cancel one of these, right? So I'll have the cosine squared left still. And one of these minus two of these makes minus one of these, right? So I'll combine these two in here. And I'll put this one over here. Now it's cosine squared minus sine squared, aha, right? If I call this x in the formula, what I have is cosine of 2x. Twice 17 degrees. So this is just a fancy expression for the cosine of 34 degrees. And I said, don't evaluate it, just reduce it to the trig function. I bring this one up because sometimes this is what happens on these harder identities. This actually is one of those extra cosine identities I said we would admit. I want you to memorize this one, that cosine 2x is cosine squared minus sine squared. But we said also note there are two more double angle identities for cosine, and this is one of them. 1 minus 2 sine squared x is equal to cosine 2x also. Let's write it. All right, so if we would have remembered this one, we could have done this one instantaneously, but this one is derived in just this method we did right here. Also, there's another one that says cosine 2x is 2 sine squared x, 2 cosine squared x minus 1. So there's actually three identities. Be aware when you do the homework problems that these things are just, some of them are just one of these two identities. I said you didn't have to memorize it. Still behooves you to recognize they look like a double angle identity. So this one's a little trickier if you didn't memorize these, but you can figure it out still. All right, so that's simplification. I hope that helps make some of this section a little easier. Okay. The other we talked about last time, maybe I won't repeat any more of those. Well, the next topic then is the next section on sum to product and product to sum identities. These are actually the least important ones. What we did was we started with the most important ones, all those ones we already knew from previous chapters that we needed for proving common identities. Then we did the sum of angles and difference of angles. Those are pretty important. And then the double angle identities, half angle identities are kind of important. You do see those in your higher math classes and your science classes. They're pretty common there. These are not so common, but they're once in a while. So on these, I'm going to say you don't memorize these. You can if you want, of course, but I'll just say on the test, if you need these, I'll give it to you, right? So if we don't need to memorize these because these are less often used, but you do need to see these because they do appear once in a while. You've got to be able to say, oh yeah, that's the product of some identity. So be aware of them, that you can convert a sum of trig functions to a product and a product of trig functions to a sum. And actually, as far as these goes, only the sine and cosine are important for these sum of product of sum identities, because they're pretty much only used with waves. And we'll have a good example, hopefully, at the end of the period using them. So here's how we derive the first one from the identity that sine x plus y equals sine cosine plus cosine sine. And the identity for sine x minus y is sine cosine minus cosine sine. Why do I do these proofs? These are actually very important for being able to remember these. When a lot of times, if you don't remember these exactly because you don't use them very often, you can figure them out quickly from this. Faster, you can look them up. And I think these make the whole thing make a whole lot more sense. So here's those two identities, plus with plus and minus with minus, we said before. What would have happened if we were to add these? I'll take the first one and add it to the second one. Then I've got sine x plus y plus sine x minus y on the left. And then I've got this plus this. Well, there's two of them, right? So I can just say it's twice sine x cosine y when I add them. And then these two cancel, right? When I add them down. And I have this. And now I realize if I were to divide this by 2 and switch sides, right? Divide by 2. So I get half on the left instead of 2 on the right. Switch sides. Then 1/2 of this side is sine x cosine y. And I get that equal to 1/2 of this side. Sine x plus y plus sine x minus y. There it is. This is a product to sum formula. Call that 4. You can take a sine of an angle, and a cosine of another angle, rewrite it as a sum of two sines. Kind of an interesting result. It's one of the surprising things about trigonometry. Now, similarly, from the other identity, cosine x plus y, let's do x minus y first, is cosine cosine plus sine sine, right? Cosine minus goes with plus. And plus goes with minus is the other one. Cosine x plus y, cosine minus sine sine. If we do the same thing, once you see these proofs, you can kind of figure out what's going on. If I add these two, then I've got the sum of these two here. I've got cosine x minus y plus cosine x plus y on the left. What's this equals on the right, this plus this. Oh, there's two of them, right? Cosine x, cosine y. So there's two cosine x, cosine y. But these cancel, right? One minus the other when I add them. Now I divide by 2 and switch sides. To get the following identity, cosine x, cosine y is equal to 1/2 cosine x plus y plus cosine x minus y. There it is. Another product of sum identity. We call that equation 5. This product can be rewritten as this sum times 1/2. Finally, if we take these two identities and subtract them, let's take cosine x minus y. Again, it's cosine cosine plus sine sine. And this time subtract cosine x plus y, which is cosine cosine minus sine sine. I subtract these on the left and I get cosine x minus y minus cosine x plus y is equal to the right. Now these cancel because I'm subtracting. And this one minus this one makes two of these. I get twice sine x sine y. Again, divide by 2 and switch sides, and see how this is just a repetitive thing. By this means you can figure these out quickly when you forget them faster probably than you can look them up in a book. So again, divide by 2 and switch. What do I get? I get this on the left without the 2, sine x sine y is equal to half what's over here. Cosine x minus y minus cosine x plus y. There's the last half angle product of sum identity I'm interested in. 4, 5, and 6. Are called aptly product to sum identities. Okay. They work for all angles x and y since everything's defined for all x and y. All right. Now, once again, if you can go from a product to sum, why can't you start with the sum and go to a product, right? I'll be able to go the other direction. If you can carry the stuff from across the yard to there, you can carry it from over there back, kind of thinking. Of course you can. From equation 4, or let's say in equation 4 now, doing more proofs than I usually will, but we are trying to learn how to do proofs, and these are important ones because they really help you remember how these things work. This is the way I'm able to remember them best, I think. In equation 4, let there be a substitution. Let alpha be x plus y over 2, and let beta be x minus y over 2. Why would we do that? Actually, I'm sorry, I want to do this a little differently. X plus y and x minus y. The reason we want to do that is that we have in here sine alpha and sine beta, and we get a sum of two trig functions, and we can convert that to a product. So we're going to make this a sum of two trig functions of two angles. Now, if I do this, then there's a conversion back the other way. You can tell by adding these. Take alpha equals x plus y, beta equals x minus y, and you add these, and you get alpha plus beta equals 2x plus 0. These will cancel. And you figure from that actually x is alpha plus beta over 2. Similarly, if you subtract them, alpha minus beta on the left is the x's cancel, and you get y minus a minus y is 2y, and you wind up with y is alpha minus beta over 2. So this is the substitution you want to make. If you let alpha be this angle and beta be this angle, then that's what x and y have to be just by solving for them. And suppose I put that into equation 4 here. Now what I got is sine x gets replaced by alpha plus beta over 2, right? Y gets replaced by alpha minus beta over 2. And I have over here 1/2 sine alpha plus sine beta, because we made that substitution. This was alpha and this was beta. Right? Now I just have to multiply by 2 and switch sides. And what am I going to get? I get twice this side is just sine alpha plus sine beta over on the left. So twice this side is over here. And then I want to put twice this side over here. Twice sine alpha plus beta over 2 cosine alpha minus beta over 2. Here's how you convert a sum of sines into a product of a sine and a cosine. So we call that a product to sum to product identity. But all you have to do is recognize if you can convert a product to a sum, then you can convert a sum back to a product, right, from the previous identity. All right, so that's this thing. Now, if you make the same substitution in 5 and 6, you can get some other identities. The same substitution in 5 and 6 yield corresponding identities for them, right? Again, x plus y becomes alpha, x minus y becomes beta, and you get cosine alpha plus beta. Cosine alpha plus cosine beta from this one. I'm substituting this for alpha, this for beta, equals this side, and x is alpha plus beta over 2. So you get and then the whole thing's multiplied by 2. So you get twice cosine alpha plus beta over 2, cosine alpha minus beta over 2. But just make the same substitution in this one. You can kind of see it if you look at it for a minute. And you get another sum to product identity. That can be 6. Oh, no, not 6. 4, 5, 6. This was 7. This is going to be 8. And then finally, for 9, you make the same substitution in this one, right? You let x plus y be alpha, x minus y be beta. So this is cosine beta minus, and actually these can go in either order. Right, cosine's an even function, so this cosine of x minus y is the same as cosine of y minus x. Take minus the angle, same cosine. I guess that doesn't matter. All right. Well, you put the same substitution in there, and you get cosine beta minus cosine alpha. That doesn't matter, does it? Is twice sine alpha plus beta over 2, sine alpha minus beta over 2. And you get identity 9. And 7, 8, and 9 now are sum and difference to product identities. And there's some more of them. Let's not write them all down. But any sum and difference of sine and cosine can be rewritten as a product of sines and cosines. That's the idea of these. It's kind of fascinating that it works with trig functions. And then there are more. Maybe what I'll do is just put up the screen here for a minute. Get this up. It's over here. Oops. If you were to Google sum to product trig identities, you can see lots and lots of formula pages where people have these online. Here's one of them. So let me put this up and I'll just try and share this screen in here. Can't get the thing out of the way. Here we go. All right, so you should see now, here's a whole flock of identities here. Not all that many, but here are the sum to product identities that they list. Here are the product to sum identities. And so there's 4 of them each that they've listed. You can use whichever one you want. And as I said, all these identities, sum to product, product to sum, are the ones you don't have to memorize because they're not used very much. It's better just to be able to figure them out like that, I think, than to try and memorize too many. But, you know, maybe they'll help you in this first test. So if you want to memorize them, do that. But I'll give them to you on this next test if you need them. Any questions on all of those? All right, so I'm going to take that back off then. And I have a good question for you. What good are all these things, right? I know it's kind of neat for a mathematician to say, hey, you can rewrite a product into sum with these functions. But what good is it? There's a few applications here that use them. One interesting thing is that if you, well, let's just do some homework here. But one interesting thing, I'll show you a video in a little bit, is if you can convert between the two, sometimes you can analyze a signal the way it's going to behave and of what you couldn't before. So we'll get to that shortly. Let me do just a couple of the problems off here because these are sort of like rote exercises, but they do really illustrate how these things work. And this is the kind of thing I would probably give you on the test, but I would give you the identities with it. And you just pick the one to use, right? So convert the product shown below to a sum. Suppose you have this one. This is a 16 sine 16x sine 11x. There's a product of 2 sine functions times a 16. I can convert that using equation 6 here, right? All I have to do is say, well, I really need a 1/2 here, so I could rewrite this as, I'm sorry. I ignore the 16 and I consider this x in this equation and this y in this equation. And I should have for this, for the product of 2 sine functions, the rest of this is 1/2 a cosine of the difference of these, cosine of x minus y, so it's cosine of 16x minus 11x, minus a cosine of the sum of these two, 16x plus 11. So there's equation 6 at work. I can take sine times sine and rewrite it as 1/2 a cosine minus a cosine. Just call this x in this equation, and this one y in this equation. And it works just like that. Now 16 times 1/2 reduces to 8 times cosine of 16x minus 11x is 5x. Minus cosine 16x plus 11x is 27x. So there's how you can rewrite that one as a difference of 2 cosines instead of a product of 2 sines. So I should say convert to a sum or difference. Well, that's the kind of thing I want you to do on the test. Is just recognize that these identities are here. So when you see a product, you can rewrite it, and you can use one of these things like equation 6 to do it.
Can you go over one of the things that are in the book? One of the examples that are in the book?
A lot of these are from the book, but which one? Do you want to pick one? I'll pick
It's
one.
example 4. I just don't know where they're getting the tangent from. It's a secant squared theta minus 1 over secant squared theta is equal to sine squared of theta.
Oh, proving an identity.
Yeah, that's like the only thing I'm having trouble with right now because it's like I don't know where they're getting the tangent from.
Okay, let me do that one at the end because it's gonna be a slightly different topic than where I'm at. So I'll finish these and then I'll look at that. Okay. I actually do want to do that more often, even as what I want to do usually is the ones in the previous sections at the beginning, and then but this time we'll do them at the end. Let's do it. Here's another example. Let's see, this was 1A, I should have said 1A. Convert the sum to a product. Sum or difference, it says. Suppose I have this one I like here, 2A. If I have cosine 6t plus cosine 4t. This is the kind of thing that happens a lot in real life. And this leads into a short video I have here. T might be time, and you might have an oscillating signal like a current or a vibration. This is how vibrations, currents work. And it includes sounds, it includes electric currents, and all those kinds of things can be written using cosines and sines. And if you have two of these vibrations going on at the same time, they have an interesting result. Suppose I was to apply this one right over here that, let's see, this one. Cosine plus cosine is 2 cosine cosine. Right? So I'll say if I call this alpha in the formula over there, and this beta in the formula, then by 8, you can rewrite this as twice the cosine of the average of these, 1 plus the other over 2, times the cosine of their difference over 2. All right, so this makes 2 cosine, well, 16 4t is 10t, divided by 2 is 5t. 16 minus 4t over 2 is 2t over 2 is t. All right. So there it is. I can rewrite this sum like this. Now, what have I done that's so great? One thing is these are kind of hard to visualize. What do these add up to? There is modern software that can plot these for you, right? You might get one of these online plotting programs. But this one you can kind of visualize in your head without having to actually even plot it up. What would this look like? And this is a useful topic in Excel. What I wish we had on there to convert this and sketch it, because the new sketch is actually an interesting thing. Because 6 and 4 are kind of close numbers. Whenever you add these with close, what we call angular frequencies, in this formula, y equals a cosine bx minus c plus d. The b in physics is often written as a little omega, but whatever they call it, b or omega, is called the angular frequency. At least the variable is time. And when these frequencies are angular frequencies are close, 4 and 6, then you get this kind of case where you get a product of cosines with very different frequencies over here. So when these are close, these are far apart. And now look what it plots like. Here's how I can, in my head, visualize this. This cosine t looks like this. We know how to plot the natural cosine. It has a period 2 pi. Let's plot, in fact, 2 cosine t. So it goes between plus and minus 2. This is the graph of y equals 2 cosine. Now, what does the other one look like that's there? Suppose I sketch cosine 5t that I'm going to multiply it by. I sketch this part first. Now I'm going to sketch this part. What does the cosine 5t look like? Well, that has right? This is the period of the second one. The period is 2 pi over b, but b is 1, right? It's 1t. So that's how often it repeats. This one, the period is 2 pi over 5. So period 2, the other cosine is 2 pi over 5. That's only 2/5 of pi, so there's 2.5 periods of this cosine 5t. That's our 5 periods of this one for every period of the other one. So it's going to go up and down 5 times between plus and minus 1. Like this. 1, 2, 3, 4, 5, something like that. And this will be the other one. Y equals cosine 5t. So the point is that the one is a big wave like that. The other one is a real fast wave. And what happens when you multiply them? This function cosine 5t oscillates quickly between plus and minus 1, right? It's this one. And it multiplies the bigger one. And so what happens when you take the product and graph it? The product of this function, y equals 2 cosine t, with this one that goes between plus and minus 1 real fast, y equals cosine 5t, oscillates quickly between plus and minus this one, right? This one, if I take, this is y equals 2 cosine t, and here's minus that function. This one will be y equals minus 2 cosine. And the product of this one with the one that goes between plus and minus 1 must oscillate between plus and minus 2 cosine t. So it starts up here and it goes 1, it goes something like that. A very interesting result. If you look at that, it goes something like this. It dries down to nothing, and then it becomes big, and then it goes, and so it's going, it's called the phenomenon of beats. Draw this very well. Let me see if I can draw it a little better. But the combined cosine waves get real small and then real big and real small and then real big. I can't draw, but that's the idea. It oscillates between these two on and off, on and off, on and off. And this is what happens when you make two sounds that are pure beats, pure tones at the same time. Your voice, if you look at it's not making a sinusoidal vibration, it's making a very jagged vibration. If you ever look on something called an oscilloscope, it'll show real jagged. And it's hard to tell exactly what's making a perfect note because it's your voice is making a combination of things that come together to make an approximate note. And so there's always this, this feeling of what is the perfect voice when you combine these notes to try and produce a note. But if you take something like a tuning fork, you see a tuning fork for tuning guitars and other musical instruments, it's a metal bar like that with a couple of tines at the end, metal pieces at the end, and you tap this metal at the end and they vibrate back and forth and they send out pressure variations through the air, which are then picked up by your ear. The variation in pressure is what your ear is detecting. And so these vibrate back and forth in a near perfect sinusoidal thing. So they make the pressure go up and down in a sine wave like this. If you vibrate one of them and it makes this kind of a wave, and you vibrate the other one with some different length times, right? So maybe this is a C note, and this is an A note or something. And it oscillates at a different frequency. If these two frequencies, angular frequencies 6 and 4, are not too far apart, then when they combine, they make this phenomenon of beats where you go up and down between together. They're on, they're off, they're on, they're off, they're on, they're off because of the combined things. And what's more, they don't make the same frequency of either of the tuning forks. When you strike two tuning forks simultaneously with the same loudness so that they have the same amplitude multiplying them, 8 times this one minus 8 times this one, or 1 times this one plus 1 times this one, at the same loudness, same amplitude, then they each make a constant tone, right? That's what these things do. You hit them and they vibrate. You can try them separately and at least vibrate separately. But when you hit them at the same time, the sound your ear hears is a note that's halfway between these two, and goes on and on, on and on. It's called the phenomenon of beats. And it can be explained then by adding the cosine waves and rewriting them, right? Because when you do two at the same time, it adds their pressure variations. And the result, though, is a product that shows you the tone actually goes on and off. And that's what your ear hears, is not the frequency of either one, but a frequency halfway of it in between going on and off, on and off, on and off. This is called the phenomenon of beats. All right. So there's an interesting result that comes out of a sum to product identity. It shows you can predict this kind of weird behavior. And here I'll try and share my screen again, and hopefully you can hear this. And let's see, share. This will be an MIT video. And it's going to first show you something about tuning forks that you can, when you strike one tuning fork, it can translate the sound to the other tuning fork only if they're the same frequency. If you take two tuning forks of different frequencies, then it can't transmit the sound from one to the other. So these are two tuning forks, so their handles are stuck into the boxes here so they can amplify the vibration here. The idea is it shows that how antennas work. That similarly, antennas, if you want to transmit a signal at one frequency, you have to transmit it to an antenna that receives the same frequency. And any other frequency, it will not create a standing wave, they call it, in the antenna. And so they'll do that. They'll show that you can transmit to an identical tuning fork the same sound by putting the boxes next to each other. But when you change the frequency by putting a clamp on one of the tuning forks, now it can't transmit. That's the idea of antennas. You have to have a right length antenna to receive the signal. Then at the end, the last experiment, you'll hear the two tuning forks with two different frequencies hit at the same time. And you'll see that you get a sound that goes on and off like we predicted. So let's see if we can watch this. Hopefully you're watching. So we did the same frequency and it transmitted the sound from one tuning fork to the other because they were the same length. Now it puts a clamp on that one, changing its frequency.
Can't hear anything.
Can't hear anything?
Same here. Same here.
Strange. Loud in here. You hear that? Well, I'll stop sharing then. Can you hear me now?
We can hear you. We just couldn't hear the video.
Yeah.
The video,
The video
was
was-
as loud as I'm speaking now. I'm surprised you couldn't hear it. I wonder what happened there.
Could you share the link in chat and we could watch it maybe after class or
hold on.
something?
It's gonna play me another video here. All right. I'll kill that one. All right, well, I'm sorry you couldn't hear that. Just if you Google up there, let's see, I should have our screen back here. I took it off here, right? Yeah. you can watch this video I was trying to show you if you just Google MIT phenomena of heat. It should show you that, that video, and you can see how when they hit two tuning forks at the same time with slightly different frequencies about the same loudness, then it makes an on and off sound, illustrating the, some of the product identity. All right, well, let's see, we've got still a little bit of time left. Maybe we can field a couple of review problems, and you have one in particular you wanted to do. And I'll say that's the end of that section. Let me give the homework on it. On section 7.4 that we just did, just do all of these 1 through 3. And you don't need to memorize the identities that go with those. I'll give you those. Okay, and then finish the ones out of 7.3 that I gave you last time, because we finished all those problems. Now 7.3, just to remind you, was 2 through 9. All these off the UCO supplement. Okay, which problem did you want to look at now? Yeah.
I actually think I figured it out. Honestly, I think I figured it out.
Okay. Anything else anybody would like to look at here then quickly, before towards ahead a little bit? I don't want to start a new section today unless I try and have to come back in 5 days and just repeat what I said. But let me repeat one of these. Here's a good example that I omitted today for lack of time, but I thought might be kind of useful. This is 7A out of 7.3, and it says this. So this is going back to the half and double angle identities. If tangent of x equals -4/3, and x is in quadrant 4, evaluate, and they ask you to evaluate 3 of these. I'll just do 1. Suppose I want to evaluate the sine of 1/2 x. This is a classic problem I'm liable to give you. Remember, we did before last time. Given one trig function in the quadrant, you can evaluate any trig function of a double angle, because once you know one quadrant and a trig function, you know all the trig functions of that angle, and you use those to do the double angles. Similarly, here, doing one trig function in an angle, I can get all trig functions, and then I can evaluate any half angle. So what you do on these problems is you first write down a half angle identity and say sine 1/2 x is equal to plus or minus the square root of 1 minus cosine x over 2. There's the half angle identity for sine. Then what you need to evaluate a half angle identity is the cosine. I don't have the cosine, I have the tangent, so I have to figure it out. But write the half angle identity and then figure out the cosine. That's how you do these. From the tangent equal -4/3, I can figure out the sine and cosine also when I also know the quadrant. What do? I might like to say, well, tangent is sine over cosine. This is the hard case of tangent. That's why I picked this, by the way. You can do this one, you can do the others easier. Tangent is sine over cosine. So maybe this is the sine and this is the cosine. Why not? Why can't they be the sine and cosine? The answer is they're not on the unit circle, right? Unit circle, the biggest you can get is 1. These are bigger than 1, both bigger than 1. What happens is if you write this as a point, as a quotient on the unit circle, then you can say, oh, that could be a sine and cosine. So what you do is you divide top and bottom in this quotient by the root sum square of those numbers. -4 squared plus 3 squared. Square root is the square root of 16 plus 9 is the square root of 25. It's 5. All right. If I divide top and bottom by 5, so I get -4/5 over 3/5. Now this squared plus this squared will be equal to 1. So I can interpret that as a sine and a cosine. Alas, there's one hitch. I can also take minus this over minus this and get +4/5 over -3/5, and that's also this squared plus this squared equals 1, so it's also in the unit circle. Which is it? It could be this point, this is sine, and this is cosine, or this is sine, and this is cosine, and both work. What I do is I now apply the quadrant. It has to be in quadrant 4. In quadrant 4, right? I drop the perpendicular. Sine is negative. The y-coordinate cosine is positive. So I need this one. Sine negative, cosine positive, right? Sine over cosine. So it's this one for quadrant 4. This one was actually in quadrant 2. So there'll be two angles also always that have this tangent. They'll be directly opposite each other. Now, once I see this, I see by dividing by the root sum squared here, I get the sine and the cosine, and now I can do anything, right? So I infer from that that the cosine of x is the bottom one is 3/5. Right? And I put that in. I write this as plus or minus square root 1 minus 3/5 over 2. Right? And is it plus or minus? Well, you have to be careful here because you say, oh, x is in quadrant 4. In quadrant 4, cosine is positive, but wait a minute, we're not doing that. We're doing the sine of 1/2 x. So if x is in quadrant 4, I compute x is between 270 and 360 degrees, right? That's quadrant 4. X though, what is 1/2 x? You divide this equation through by 2 and get 1/2 x is between half of this, 135 degrees, and half of this, 180. This is in quadrant 2, right? Right, 90 to 180 is back in quadrant 2. So I'm evaluating the sine of an angle in quadrant 2. If x is in quadrant 4, 1/2 x is in quadrant 2. So in quadrant 2 now is sine positive or negative. I figure it out. Right, over here, sine, the x coordinate is positive, right? So I'm going to choose the plus sign, saying 1/2 x actually has to be in quadrant 2, even though x was in quadrant 4. All right, so I've got square root 1 minus 3/5 over 2. Am I finished?
No, it's just, I dropped them out of my pocket.
So I'm not finished. I just want to, I have a quotient of quotients. I have to reduce this. That'll be a point or two off, probably 2 on this one. I'll multiply top and bottom by the denominator that I see, 5. I have to do both top and bottom, or I'll change the quotient. And now what I've got is the square root of 5 minus 3 on top, this times this and this times this, over 10. This is the square root of 2/10, or better yet, the square root of 1/5. I reduce it, and then 1 is a perfect square, so I'll write it as 1 over the square root of 5. This is a good answer. I'll take that on the test. On the back of the answer sheet there, though, they're going to rationalize it, multiply top and bottom by square root of 5 and call it square root of 5 over 5. Either one of these is a good answer then. And that's how you can do those. Those are pretty tough problems. I thought maybe it was worth doing one of those. Try all those problems in 7.3 and 7.4. They should all be amenable now to what you've learned. And bring some questions on for the beginning next time, and we'll do a couple more of these, and then we'll charge ahead of the last section in chapter 7. How about that? Which is probably the harder part, solving equations. It'll probably take us more than a lecture. Thank you very much for coming in today.